My name is John Wu, and I'm going to be talking about this ArrayUDF. I specifically want to mention Florian Russo and Wei Zhao. They're working on this astronomy problems that's very similar to searching for variable stars. There will be, I guess Wei Zhao is not officially coming back this summer, but will still be working with us on this problem. I guess he can't get rid of us now. This has some similarity to the XPOT work that, in a sense, we're trying to take advantage of the structure of the data that's present in the scientific data. Okay? So in scientific data, most of the time people are still writing custom programs that's, with all the data management tasks and analysis tasks. And what most of the big data projects are doing is this concentrating all the data management tasks into one system, then have the user write their own analysis programs. And this is a good approach. I'm gonna skip this. This is a good approach, except when you deal with scientific data that are not stored in key value pairs, right? Most of the scientific data, as our host here know, that are stored in arrays and in files, they're not in database systems. How to deal with them effectively, that's the task we're trying to deal with. And the gist is we're going to try to take advantage of the structure of the data, right? So we mentioned we have arrays. And most of the time when we work on arrays, we're looking at neighboring cells in the arrays. And that's what we mean by structural locality. Okay? So they're present. They're by definition of the array. They're next to each other. And this is a typical 5-point stencil that you might see in a standard textbook, right? So with a higher dimension, you have similar type of structure. So the structure in the array is what we're trying to take advantage of. And what this illustrates is if you have a two-dimensional array, you have 4 processors, you can decompose them. And remember, we have this neighboring cells we need to deal with, but the neighboring cells only needs to be dealt with at the boundary of your data partition, right? If you partition your data rationally. And this is very, very different from if you just have key value pairs, you sort the tuples, and then you're trying to figure out where are the neighbors, right? Then what you end up is you have to deal with complicated joins, and that's going to take a really long time. I was going to say forever, but it never takes forever. It just takes a long time. So I'm going to not talk too much about this, except to give you two sets of examples. One is on a single processor where we have more systems that we can test against. I probably am not going to spend a lot of time dealing with each of this example system that we have tried. Wei Zhao is here, and I can talk to you as well a bit more about the details. The bottom line is, we can do a lot faster. The reason we can do a lot faster is because the data has this structure. Most of the database systems, data management systems, do not take advantage of. And in order for those systems to take advantage of those structure, they have to do self-joins. In many cases, this is very complicated self-joins. So that's essentially a single node case. This is a parallel case. In parallel case, we deal with larger data. With larger data, we have potential of much bigger improvement in terms of speed up. If you have really large data, then we're comparing against Spark. Spark does a lot of replication because this is very complicated to join. Then it runs out of memory. Okay, so it doesn't have. I guess we should have a better color scheme. Basically, Spark didn't run complete. Okay, so on this problem that Spark did complete, and we're thousands of times faster than Spark. Okay, so that's the gist of this. There's a paper that you can get, and I presume the slides are going to be available, right? So that's why I'm putting more information in there than I could talk about, so you will have the information. But in terms of summary, what we do is we're defining a way to take advantage of the structure of the arrays to handle the common stencil type of operations. And this stencil type of structure is what we call structural locality, and that's what we're taking advantage of. Okay. Thanks.
Thank you very much.